Figure 12, now we're looking at the gradient at any point, and this is where it becomes interesting, because we no longer want the gradient of the graph like the average gradient, so we can have two coordinates on a graph. We want the gradient at a specific point, and this is where it really becomes interesting. Okay, so let's say this is our graph. It really doesn't matter how it looks like for now. And let's understand this. The gradient of the graph and of the tangent at any point, they are equal. Okay? So let's assume you've got a tangent to that part of the graph. Its gradient is the same as the gradient of the graph at that point. How to calculate it? Okay, so let's start with the basics. We are assuming we've got 2 points. This is point number 1. And for now, just forget about the tangent. And somewhere we have a point 2. And we can define this as x. And we need to define the second x coordinate as well. Now, per definition, we are going to call this distance h. So technically, this x would be x plus h. Okay, now keep that in mind. And if we write down our expression, again, this is function f. If we write down our expression for the gradient, it would be function of fx where x is 2 and fx where x is 1 divided by x2 minus x1. Okay, but now we have it looking like this. So this will be x2 is x plus h and x1 is x. x2 is x plus h and x1 is x. Let's take it one more step. One step further, you'll see that x minus x becomes 0, so it's just an h. And this is where the challenge comes in, okay? Because if we want the gradient at a specific point, like what I've explained with the tangent, right? We need to get this, like we can currently get the average gradient between point 1 and point 2, right? But if we close the distance of h to a 0, then x1 and x2 will be the same coordinate, right? Which will give us, if we use the method of the average gradient, which will give us the specific gradient at that point. So we want h to become 0. But that's where the problem is. H cannot become 0, because if you look at this definition, or if it becomes 0, it can become 0, but if it becomes 0, this whole thing becomes undefined, this whole expression, because we are dividing by 0 there. And that's where the challenge lies. And that is where limits comes in, okay? Because we know now, okay, we cannot make it equal to 0, but we can approach 0, right? And this is the formal expression for the gradient, okay, of a function at any point. And remember, we've used the average gradient method now, but this is how it will work out. So f accent x what that means, it means the derivative. That means the expression for a gradient at any point of the graph, okay, is equal to the limit where h approaches 0 of f of x plus h minus fx divided by h. So mathematically speaking, this is perfectly fine now, right? So we have the limit where h approaches 0 for the expression of the average gradient, okay, and that is equal to the derivative. Now, if we want the gradient at any specific point, we just substitute the x value in, and we'll have it. We will be able to calculate it. Okay, so this is how, theoretically speaking, how the gradient at a specific point works. Okay, so this is all good and well, but how do we apply it, right? So there's two methods. The one is something called first principles, if you know when to work with this. So that's the theoretical foundation. And then the other one is also based on first principles, where they substitute the x value in from the start. Okay, so we are going to take the exact same equation as previously. We are going to say that fx is equal to x squared minus 3. And now we want the specific gradient where x is equal to, let's make it 5. Why not? What is the gradient for on this graph where x is equal to 5? I'm going to show you the method I prefer above the method that's in the textbook. Okay, both of these are in the textbook. Many people, when they want a specific gradient, they immediately substitute the 5 into x's place in our expression. I do not, well, there's nothing wrong with it, but it might be very confusing. So I'm going to show you how to do it based on first principles anyway, and that will make life much easier. Okay. So first things first, remember you have to write down the limit h approaches 0 every time. And wherever, just to explain, this is now fx, so wherever there's an x, you have to put in x plus h, now with the first expression, okay? So this is x squared, so this becomes bracket x plus h squared minus 3, because of the negative 3 is still there, close bracket, negative, new bracket, x squared minus 3, and all of it over h. Remember the h, okay, it's easy to forget it, okay, so don't. Then I'm just creating a little bit of space. Now we just need to simplify, okay, so x plus h, sorry, that square should be outside the bracket. X plus h squared becomes x squared plus 2xh plus h squared minus 3 minus x squared plus 3. Okay, I'm just continuing on over here. So now this x squared minus the x squared, it falls away. So we're only left with 2xh plus h squared, negative 3 plus 3, so it becomes a 0. Okay, so this is what we are left with. And remember, we want at the end, we want to get rid of the h. So that's what we're going to do now. We're going to factorize at the top. So it will be 2x plus h. Factorize the h out. They cancel out. So now you are left with an expression that looks like this. Now we can let h approach 0. Okay, so h approaches 0 now, so this whole expression becomes 2x. So what do we have here? We have the derivative of the function. Okay. Now, if we want the gradient where x is equal to 5, like we've stated in the beginning, now we just put the 5 into the expression. So our gradient at that point is equal to 10. So this is how you calculate the specific gradient at any point. We can talk through it once more. Remember, we start off with the whole principle that we want to have h approaches like equal to 0, but we can't, therefore we have to use limits. Okay? Otherwise it becomes undefined. Now we use this expression, we substitute in x's place the x plus h. With the expression over here, we just leave it as is because fx. We simplify all the way to here. We want to get rid of the h. Therefore, we factorize to get an h at the top. If you can't do this, you made a mistake. Okay, then you have to check you've made a mistake somewhere. And then we have a simplified expression. Now h can become 0, so we're only left with 2x. And this is the derivative of the function. We want the gradient at the specific point. We substitute x in, we get our answer. Okay, and that's how it works. The next video will be about the first principles now. You calculate it in a test when they ask you about first principles.